Hi everyone, welcome to my next video on calculus, my series on calculus. We're now going to move on to the next half of calculus, which is integration. So let's just quickly recall. We said right at the very beginning that when we plot a graph, it often tells us the basic information of the two variables that are plotted, but it often gives us much more information than just that. So we gave the example of a velocity time graph. Obviously, you look at a velocity time graph and you can read off the velocity at different times. But if you measure the slope or the gradient of the graph, it will give us the acceleration. Or if we work out the area under the graph, then that gives us the distance traveled. Now, up to now, we've done calculating the gradient, so we've worked out things like the acceleration on a velocity time graph. But now we're going to move on to the next bit, which is actually calculating the area under the graph. And we call all of this integration. So let's first of all think about how we could calculate the area. At school, you probably did some work where you drew a graph and you tried to calculate the area under a graph, or maybe you calculated a funny shape and you had to calculate the area of a funny shape, and you may split it up into little squares, and then you counted up the squares, and maybe some were half inside and half outside, and you counted those, and some were mostly outside the area, so we didn't count those. You probably did a kind of rough calculation by adding up squares, and that can be a very good approximation for the area. With integration, it's quite similar. It's not exactly the same. With integration, the whole process, although you can't really see it, is actually splitting up the area into little rectangular strips. And basically, the thinner the strips, the more accurate the area is going to become. So if you look at those three diagrams there, the first one, we've got quite wide columns, which are 2 squares wide. The second graph has columns which are just 1 square wide, and the third graph has columns which are half a square wide. And if you look at the actual area of those columns, it's getting closer and closer to the actual area under that curved line. Now, that's basically what calculus does. So it may not appear obvious when you're doing calculus, but that is really what we're doing. We're making tiny little strips, and we're making those strips narrower and narrower until they become infinitesimally thin. So they're actually they basically have no thickness. And then you get the exact area. That's basically what Isaac Newton and Leibniz did hundreds of years ago when they worked out calculus. Right, so now we're going to look at how we actually do the process of integration. You need to know a few bits of notation. So when we worked out the gradient equation using differentiation, the derivative, we used to have this symbol dy by dx. And when we worked out the derivative, we started off with the original equation, and then we wrote dy by dx equals, and then we differentiated. That's what we did first of all. Now we're doing integration, and with integration we have a different symbol, and it looks a bit weird. It's this kind of long curly s, and then y dx. So you're going to write that when you work out the area equation. And just like with when you do the derivative, sometimes it could be dv by dt instead of dy by dx. Similarly, you can have integral of v dt instead of integral of y dx, or it could be different letters anyway rather than y and x, but most of the time it's going to be integral of y dx, or curly s, long curly s, y dx equals. And the long curly s is really like a stretched letter s, and you could think of it as being the sum of all the little thin strips. You're not going to see any strips. It's just a way of notation to show what we are doing when we're doing integration. So if, for example, that curly s y dx basically means integrate y with respect to x. I don't know whether that makes a lot of sense to you, but we're looking at the x's in the equation and we're changing the x's. So with differentiation, we and multiplied the power by the number in front, and we reduced the power of x by 1. This time we're doing a similar thing, but we're looking at the x's anyway, so it's integral of y dx. So here's an example. This is a type of question or an area. Integral of 4x squared minus 7x plus 1 dx. So the dx bit on the end, it may be a bit annoying, but all it's doing is when we integrate this equation, we're looking at the x's. So it just means integrate the equation. You just have to write dx on the end. It might be a bit annoying, but that's what it is. Right, so now I'm going to teach you how to integrate. And so obviously what we're doing when we're integrating is we're finding the area equation, and that's going to be called the integral. Now, just like when we did differentiation, we have to change the original equation into a new equation by following a pattern. And now this pattern we have to use, this is the interesting thing about it, is the exact reverse of doing differentiation. And that's really important to remember that, because it will help you when you're doing it to get it right. So here's a look at an example. If we had y equals 4x squared minus 6x plus 7, and we differentiated it, that's what we've been doing up to now, it becomes dy by dx equals 8x minus 6. Now, since integration is the reverse of differentiation, if we started the other way around, if we started with y equals 8x plus 8x minus 6, then when we integrated it, it would go back to 4x squared minus 6x plus 7. There's only one issue, is that how are we going to get that 7 from the original equation? And for this reason, we have to end up putting a plus c at the end of our solution, because there could be a number that reappears. Remember when you differentiated, numbers disappeared? Well, now we're doing the reverse, so numbers need to reappear. That can be a bit annoying, having to put plus c on the end each time, but actually it doesn't really affect how we calculate areas in the end. So although it's a bit annoying, you will see that it doesn't actually stop you calculating areas. So let's actually do some integration. So in differentiation, we had to multiply the number in front by the power of x to become the new number in front, and then we had to reduce the power of x by 1. Well, integration is the exact reverse. So in integration, we increase the power of x by 1, and then we divide the whole term by this new power. Now that rule may not at first sight be exactly opposite to the first rule we had for differentiation, but if you try it, you'll see that it is actually the reverse operation. So let's just have a look at that's the rule written out in algebra. So if y equals ax to the n, then we're going to increase the power of x, so it becomes ax to the n plus 1, and then we're going to divide the whole thing by n plus 1. So let's do an example. Here is y equals 2x squared minus 7x plus 4. So we're going to basically write integral of y dx equals, that means we're finding the area equation. And then we look at the first term. Now the first term is 2x squared, so we need to increase the power of x, so it becomes 2x cubed. And then we've got to divide all of it by this new power, which is 3. So it's going to become 2x cubed over 3. If we go to the next term, minus 7x, that's going to become minus 7x squared. We're going to increase the power by 1. And then we've got to divide it all by the new power, which is 2. So it's minus 7x squared divided by 2. Now what happens to 4? Well, if you think back to differentiation, x terms became numbers. So now we're doing the reverse. Numbers are going to become x terms. So 4 will just become 4x. And one last thing, we must remember to put a plus c, because numbers should be reappearing. So we need to put a plus c on the end. And that's how you integrate. Now there are a few things I want to make sure you don't miss. So the first thing is, each term is basically becoming more complicated. They're becoming a higher power. So x squared terms are becoming x cubed terms. X terms are becoming x squared terms. Numbers are becoming x terms. Everything's becoming slightly more complicated. The second thing to remember is that numbers don't disappear like they did with differentiation. They now become x terms. The third thing is we mustn't remember the plus c, mustn't forget the plus c. So we always end up with one extra term every time we integrate. And the last thing is we could actually check this answer by differentiating it and seeing if we get back to 2x squared minus 7x plus 4. So that's quite a useful way to check your answers and make sure that you are doing it right. So if we look at the first term, 2x cubed over 3, we'd need to multiply the power by the number in front, it becomes 6, and reduce the power by 1, so it becomes 6x squared over 3. Now 6x squared over 3 is actually 2x squared, so that is correct. And you can work it out for all the others. So we've now basically learned the rule of how you integrate, and we're going to do some practice of that in a moment. How do we actually find an area? Well, we're going to look at that in the next video. It's not very difficult. We've almost done it, to be honest. Once you've found the area equation, you're nearly there. But the thing you have to do is you have to put limits into the equation. We need to know where you want to work out the area under the graph. We're not really explaining that in this PowerPoint, and it's called definite integration, but we're going to do that in the next PowerPoint. So basically, this is what we've done in this whole presentation. We've basically said that to find areas under curved graphs, we're going to use integration process, and the area equation is known as the integral. The integral is usually written as integral of y dx equals, and the basic rule is you need to increase the power of x and then divide the term by the new power. Okay, so let's just do 4 questions, so make sure you get the hang of it. So the first question we've got here is y equals x squared plus 3x plus 1. So the first thing when we're integrating this, the first thing we do is to make sure we write integral of y dx equals. Always write that when you're starting an integration question. Then we look at the first term. We need to increase the power by 1, so it becomes x cubed. And then we divide by the new power, so we divide by 3. So it becomes x cubed over 3. The next term is going to become 3x squared divided by 2. And then the 1 is just going to become 1x. And you mustn't forget the plus c at the end. So that's how you integrate. But sometimes these fractions can be simplified. Let's look at the next question. Y equals 4x squared plus 2x plus a half. So it's integral of y dx equals. The 4x squared becomes 4x cubed over 3. The next term becomes 2x squared over 2. Now we can simplify 2x squared over 2. It just becomes x squared. And the half becomes half x. And we can put a plus c. Now my half x I've just written as x over 2, but you could just write it half and then x next to it, and then the plus c. The third question, y equals 2x squared over 5 plus 7x over 2. So we first of all write integral of y dx equals. Now we increase the power of x, it becomes 2x cubed, but we've got to divide this by 3, and we're already dividing by 5, so it ends up being dividing by 15. So it's 2x cubed over 15. The 7x over 2 becomes 7x squared, but we've got to divide by 2, and we're already dividing by 2, so we divide by 4. 7x squared over 4. And we mustn't forget the plus c. And the last example, we can't do this question as it is. We have to rewrite the question because we've got x's on the bottom of fractions. So we need to move the x squared onto the top of the fraction, so it becomes 5x to the minus 2. And the second fraction is going to become 7x to the minus 3 over 2. Now we can integrate it following the rule. First of all, we write integral of y dx equals, and then we need to increase the power of x. It becomes 5x to the minus 1, and then divide it by that new power. So we divide by minus 1. So this changes the whole sign of the whole term, so it becomes minus 5x to the minus 1. And the other term, again, we increase the power, so it becomes 7x to the minus 2, and we need to divide by minus 2, so it becomes 7x to the minus 2 over minus 4. That minus 4 on the bottom is now going to change the whole sign of that whole term, so it becomes a minus 7x to the minus 2 over plus 4. I hope that makes sense. And then we need a plus c on the end. That's quite a hard question. Right, the task I want you to do is look at your notes on page 15, and you've got a whole load of questions on page 15 of how to questions to integrate some equations. Please have a go at questions 1 to 10. Questions 11 and 12 you don't have to do, but they look a bit harder. They say they're harder ones. They actually aren't really harder, but you just have to do a little bit of algebra before you then do the normal integration. Do remember to write out integral of y dx equals. Do follow the rule. Don't forget the plus c. Remember that numbers don't disappear, they become x terms. And do remember that you can check your answers by differentiating them, and they should go back to the original question. Thank you, that's it.